Okay, so I've started the recording. So at this point, so that I get your record for attendance, please type your name in the chat for attendance records.
This meeting is.
Okay.
Is it get it or leave it? I didn't get
So
it.
if we'll do this, you type your name in your chat for the attendance records. You can do it now. You can do it at any point during the class today. Okay, great. So thank you for that. Okay, let me go mute everybody. All right. So I hope everybody had a good week. I hope you're all doing well, ready for class today, and that you'll have a good weekend after this. So we're mostly going to finish up with our statistics today. So we'll go over the last parts about measures of dispersion, and we'll basically finish up the statistics unit today. We'll do a little reminder and summary next week, but after that we'll be done with the statistics unit, and we're going to move on to geometry, which is going to be the next unit. But we have some pretty important parts of statistics to still finish up today. Okay, but maybe before we do that, so once again, a reminder: please type your name into the chat. Otherwise, I won't have your record for attendance. Okay. So there was only one homework problem, and it was a little bit tricky, but I saw that one or two people submitted answers on the WhatsApp chat, and the answers were correct. So, and I think at least one of those people is here right now. So would anybody like to demonstrate this problem for everyone? So two numbers, x and y, have a geometric mean of 12 and an arithmetic mean of 12.5. Find x squared plus y squared. And let's, maybe even before we start the answer, let me just recall that the arithmetic mean is going to be x plus y over 2, and the geometric mean is the square root of x times y. Okay, so anyone would like to demonstrate how to do this?
Yeah, but
yeah, Gabriel.
Yeah.
Mm-hmm.
So for the question,
yeah,
we see that the geometric mean was given for the two value as 12.
So sorry,
we will say the root of x y is equal to 12.
Okay, so sorry, let me, I wasn't getting you so clearly there.
GM will be equal to root of x.
Mm-hmm. Okay, right. So we set these equal to 12.5 and to 12. Great.
So, yeah.
Mm-hmm.
So for the AP, the first question, if you cross multiply, you get x plus y equals 25.
Okay, great. So let's just do these step by step, right? So we get, so this gives us x plus y equals 25. Great, carry on.
That gives us equation 1.
Okay, so x plus y equals 25. So what do we do next?
Then we keep that equation and move to the geometric mean.
Mm-hmm. So right. So you have geometric mean here?
The square both sides.
Okay, great. So we square both sides there. So let me just use these arrows over here. So squaring both sides from the geometric mean, right? Good. So that gives us that xy
equal 144.
Great. Okay, and so then what's next?
So what I did, for me, I took the second equation, I divided both sides of the equation by x.
So both sides of this by x over here?
Yeah.
Okay.
So that gives you y equal 144 over x.
Okay, so y equals 144 over x. Great.
Then I took the first equation and substituted the value for y.
Okay, so we do a substitute, right? So substitute. And then we get, so x plus 144 over x equals 25.
Yeah, so if you find the LCD.
Yep.
If you find the LCD, you get x squared plus 144 equals 25x.
Right, so x squared plus 144 over x equals 25. which tells you that x squared plus 144 equals 25x.
So if we prove the in terms of quadratic
Yep,
expression, if we prove
25x
the in
plus
terms of
144.
quadratic, yeah,
Mhm.
so that from 144 equals 0.
Right. And so what is this? How does this factor? So if we get x squared minus 25x plus 144 equals 0, how does this factor?
So I open two parentheses.
Mhm.
And I distributed the x. There are four factors of 144.
Mhm.
And the two factors of 4 was 9 and 16.
Great.
So
So
in the first parenthesis, it will be x minus 9. And next one will be x minus
Mhm. Great.
So solving for x will be equal to 9 or x will be equal to 16.
Great. Okay, so x is equal to 9 or x is equal to 16. And then, of
So
course,
we can use the equation.
Mhm.
Yeah. So since we put a value for x, we can find y by using the equation that says y equal 144 for x.
Right. Since y equals 144 over x, right, then we get y equals 16 or y equals 9, right? Yes, it's just if whichever one the x is, the y is the other one, right?
Hello.
Hello, yes? So Gabriel, you want to just finish up? So now we know what x is and we know what y is. So the answer.
So what are they about?
Yep.
Yeah. So
Yep.
so they are told the x squared plus y squared and the everything
Right. Okay. So sorry, I'm not getting you so clearly right now. But at this point, we just have to plug it in, right? So this is just going to be 9 squared plus 16 squared, right? And this is going to come out to 81 plus 256.
Yeah, so they are so the x squared plus y squared repeat.
Mm-hmm. So sorry, the connection is not so good. I'm losing you right now. But I mean, at this point, you've basically solved the problem, right? If you know what x and you know what y is, then x squared plus y squared, you just have to substitute in 9 and 16, and you get 9 squared plus 16 squared, which is 81 plus 256, and this is going to be 337, right? So this is the right answer. The right answer is 337. So, and this is perfectly, this method works and is completely correct. Now, I was wondering if anybody saw, the key is we use these two equations, right? X plus y equals 25 and xy equals 144. Did anybody find a way to find x squared plus y squared without individually finding x and y first, but just finding the expression x squared plus y squared kind of by itself? I think I saw somebody posted something to the chat that had a solution that did this.
Yeah, my network bow.
Yeah, Gabriel?
I was experiencing bad network.
Yep. Okay, yeah. Let's try. Right. I'm not getting you so clearly, but we'll try. Okay, yeah. How do we do it? Let me just do a new page. I'm just going to write a new page and I'm going to carry. So I'll say alternatively. So alternatively, well, we know x plus y equals 25, and we know xy equals 144. And we want x squared plus y squared, right? So what's a way to get that without actually solving for x and y individually?
It's about squaring It's by squaring x plus y equals 25.
Exactly, right? So if we square x plus y equals 25, we get x plus y squared equals 25 squared, which is the same thing as saying x squared plus 2xy plus y squared equals 625, right? That's 25 squared there. And so now, if what we want is x squared plus y squared, but what we have is x squared plus 2xy plus y squared, what's the last step that we have to do? Well, what we can do, right, is just subtract 2xy from both sides. And we know what xy is. It's 144, right? So we can subtract 2xy, and on this side, we can subtract 2 times 144 because they're the same thing. And what do we get here? We get x squared plus y squared is going to be equal to 625 minus 2 times 144. And if you work this out, this comes out to the same answer. You get your same 337 over there. Okay. So this is like a little bit of a faster solution because you don't have to solve individually for the x and the y, but the other solution is completely fine. You know, it's the other solution is it works. It just takes a little bit longer because you have to solve for x by itself and you have to solve for y by itself. Okay, but this is great. So thank you, Gabriel. Absolutely correct. The answer is 337. Any questions on either of the methods for doing this problem? Yeah, James?
Yeah, the next step you guys use to solve for the problem is kind of confused about it because on x plus y is equal to 25, which is the equation of the first equation of x, and x times y equals 144. Then now you have to square the first equation.
Right.
And you know x squared plus 2xy plus y squared. So that means 2x is the same as the value of x. X times y equals 144.
Yeah.
So that means it will be 2 times 1.
Sorry. Yeah. Yep.
Yeah. So that means it will be 2 times 144 will be as 2. It will be equal to 2xy.
Right.
Yeah. Sure. I'm confusing about because if 2x is equal to 144, then you say 2x is equal to 44, 144.
No 2x. Only all that I have is that xy is 144. So here I have 2xy. So 2xy here is equal to 2 times 144, right? So on this side, I can subtract 2xy. But since xy is 144, I can, on the other side, I can just subtract a number. I can subtract 2 times 144, right? There's no 2x. There's just 2xy.
So that means we're getting rid of 2xy from the problem, and we have to get rid of the value from the equation on the other side.
Exactly.
Okay, I understand. Thank you.
All right.
Yeah, sure.
Yes, is that Prince?
Yeah. Okay, my issue has to do with the 25. The 25, the x plus y equal to 25.
Right.
How?
Oh, well, so this is from the beginning, right? So we know that we're given that the arithmetic mean of x and y is 12.5. And remember, with two numbers, the formula for the arithmetic mean is x plus y divided by 2. So we have x plus y divided by 2 is 12.5. And so the first thing that we did is we multiplied both sides by 2. And that's going to cancel out the minus 2 here. So on the left side, we'll get x plus y. And on the right side, we get 12.5 times 2, which is 25. Is that okay?
Yeah.
Okay, great. And same with how we got the xy equals 144. We start with this geometric mean equation. We have to square both sides to get an expression for xy. Okay, great. Is everybody okay? Any more comments on this problem? Or should we move on? Okay. All right, well, let's move on to the actual statistics. So Okay, so today I want to talk about these measures of dispersion. Okay, we've done all this measures of central tendency. We talked about the mean and the median and the mode and some of these other things, geometric mean, harmonic mean, that have some uses sometimes. And so what I want to do this time is talk about measures of dispersion, which are not about finding like a typical entry in the data set, but instead they're about seeing how much the entries vary, right? So for this, I have two different data sets over here. So here's one of them. 9.9, 9.9, 9.9, 10, 10, 10, 10, 10, 10, 10, 10, 10, 10.1, 10.2. Okay, so this is a data set that is has a lot of entries, and most of the entries are very close to 10, right? Now here I have another data set, minus 10, 1, 10, 24, 25. Okay, so this is a data set that looks very different from the first data set, right? But in fact, if you calculate the mean and the median of both of these data sets, you get 10 for both of them. I'm not going to do the calculation, but this is an exercise. If you try to calculate the arithmetic mean of this data set, you get 10. If you calculate the median, you get 10. That's maybe pretty easy to see because it looks pretty clear that 10 is in the middle here. And then over here, if you calculate the mean, you will also get 10 because the numbers will add up to 50 and you'll divide by 5. And then the median, of course, is the third entry out of 5. And so that's also going to be 10. Okay, so both of these have mean and median equal to 10, but this looks a lot different from this one, right? This data set is somehow it's more dispersed. And this one here is less dispersed. Okay. Okay, so what we want is statistics that will show us the difference between these two sets, right? And the mean and the median are not good enough to show us this difference, okay? We're going to need other measures that are going to show that this is somehow it's more widely distributed, it's more dispersed than the first data set. And so we have three measures of dispersion that we're going to study. There are several more that we're not going to talk about. There will actually be a fourth that we'll mention a little bit later. But so the main things are the range, what's called the mean absolute deviation, what's called the standard deviation. And this is somehow, the most important one and the most widely used. Okay. So let's just start defining these. We'll start with the range, which is the most basic one. So the range of a data set, which was mentioned, I think, a couple weeks ago, it's simply the difference between the largest entry and the smallest entry. So it's a very, very crude measure of dispersion. It doesn't tell you that much. It just tells you how much more is the largest measurement than the smallest measurement. So in the data sets above, the range of the first data set, well, what is it? The largest entry is 10.2 and the smallest one is 9.9. So you're going to get 10.2 minus 9.9, which is 0.3. And likewise, for the second data set, the largest entry is 25 and the smallest entry is minus 10. So the range is just 25 minus 10, which is a range of 35. Okay, so these are just the calculations right here. So the range of the first data set is just this 0.3. And the range of the second data set is 35. And of course, 35 is bigger than 0.3. So the second data set has a bigger range. Okay, and a bigger range generally means more dispersed. It means that the entries are more all over the place. They're not as uniform or as consistent, these measurements in the second data set as they are in the first one. Okay, so the range is pretty basic, very, very easy to calculate. You don't really need a formula. It's just largest minus smallest. Okay, any questions about the range? Yes, Prince. Oh no, James?
Yeah.
Yeah.
I don't like the range. For the first data, you were saying that they have the means of 10. They both have the means of 10. I don't understand what you really mean by that.
So sorry, can you say the question one more time?
I said that you are saying that the both data entries have the means of 10.
Mm-hmm.
So I don't understand because looking at the first data, you're having like 1, 2, 3, 4, 5.
Yeah.
And
So
in the second data, yeah.
right.
So I'm
So
not
I
really
mean, the mean just means if I take the average of all of these data entries, right? So if I do 9.9 plus 9.9 plus 9.9 plus 10 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 plus 10.1 plus 10.2, and then I divide it by the number of entries. So in this case, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 entries. So if I add these all up and I divide by 14, I'm going to get 10. And here, if I add these all up and I divide by 5, I'm going to get 10. It just means that in both cases, 10 is the average. Even though here I have lots more measurements and the range is much smaller, the average is still going to be 10 in both of them. And so the reason I'm saying this is that I want to say, like, these two sets look different, even though they have the same mean and the same median. So we need other measures that are going to be able to tell us the difference between a data set like this and a data set like this. And so and these are what are called the measures of dispersion, and the first one is the range. So I'm not sure, does this answer your question or not?
Yeah, it answered my question, but I got another question again.
Okay.
Yeah, so that means looking at the measure of dispersion, that's by having the same means, but we look at the range to show the differences, right?
Exactly.
Okay, thank you.
Okay, yeah, you're welcome. I mean, of course, they could have different means also, but I'm just saying, like, even when they have the same means and even when they have the same median, there's still differences between these data sets that we want to capture. Okay, other questions about the range? Okay, so let's move on to the next one. This is the so-called mean absolute deviation. So this is the definition. So if we have a data set with a bunch of entries, x1, x2, all the way up through xn, and let's say their mean is x bar. This is a very common notation for the mean. You put x with a bar over it. So what is the mean absolute deviation? By definition, it's the average of the numbers xi minus x. So for each data entry, you look at its distance from the mean, right? When you take the absolute value of a difference, this is the distance from xi to x bar. So it's the average distance from one measurement to the mean. Okay? So, and this is what's called the mean absolute deviation. It's saying, on average, if you take a measurement, how far away is it from the mean, right? So it's telling you how dispersed these things are. If the mean absolute deviation is big, that means a lot of your measurements are really, really far away from the mean. Whereas if the mean absolute deviation is small, then most of your measurements are close to the mean, right? And saying that on average, you know, the distance between each measurement and the mean is not so big. And so we're going to see from these two data sets over here that in this case, most of the measurements are very close to the mean, right? The mean is 10 and everything's close to 10. So this should have a small mean absolute deviation. And over here, most of our measurements are pretty far away from the mean. So this one should have a larger mean absolute deviation. I mean, okay, we have one that's exactly the mean, but these other ones, 24, minus 10, 25, these are all pretty far away. Okay? So let's actually calculate, let's calculate this for the two data sets that we had. So the first previous data set, let me just copy it down. It was 9.9, 9.9, 9.9, 10, 10, 10, 10, 10, 10, 10, 10, 10, and then 10.1 and 10.2. Okay? So this is our data set. So first we have to calculate the mean, this x, which I'm just going to tell you is 10. This is an exercise to calculate the arithmetic mean here, but you just add these things all up. Maybe I should mention that the number of measurements, this n right here, is 14. Okay, so if you're trying to figure this out, this is 14. Okay, so now how do we do the mean absolute deviation? Well, you have to take all of the measurements and look at their distance from the mean. So what we're going to do is we're going to start. So what do we have to do? We have to take the average of all of these numbers. So what we want is the average, or the arithmetic mean, the average of, what do we have? We have 9.9 minus 10, and then 9.9 minus 10, and then 9.9 minus 10, all absolute value, then 10 minus 10, 10 minus 10. Maybe instead of writing them all out, I'll just say 10 minus 10. How many times are we including this? 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So this is going to be 9 times. And then 10.1 minus 10. And lastly, 10.2 minus 10. Okay. And so now we can figure this out. So this is the average of, well, here, this is 9.9 minus 10. That's negative 0.1, but it's absolute value. So we just get 0.1. So it's just 0.1. And then that's going to happen 3 times. So 0.1, 0.1, 0.1. Then 9 times we just get a 0 here, right? So 0, 0, 0, 0, 0, 0, 0, 0, 0. And then here we have 10.1 minus 10 and 10.2 minus 10, right? So we get 0.1 and then 0.2. And so what is this average? This equals 0.1 plus 0.1 plus 0.1 plus a bunch of zeros, which don't matter, and then plus 0.1 plus 0.2, all divided by the number of entries, which is 14. And so this turns out to be, when you add it all up, this is 0.6 divided by 14, which comes out to be 0.043, roughly. Sorry, yeah, close enough. Okay, so in this case, the mean absolute deviation is going to be about 0.043. Okay? Okay. So for the mean absolute deviation, it's a bit of a multi-step process. You first have to calculate the mean. That's going to be 10. Then you have to do, for each data entry, you have to look at its distance from the mean and look at the absolute value of the difference. That's how you calculate it. So now you get a new data set. And now you take the average of that data set, and that's going to give you the mean absolute deviation. So in this case, the mean absolute deviation is 0.043 for the first data set. So we'll do the second one also, but before we do the second one, are there any questions about how we do it for this first one?
Yeah.
Yes. James.
Yeah. Like in the case, I want to ask, like, for example, you having the means to be 10, and each entry appeared there 14 times. Can you say 10 times 14 minus the total of the data entry?
Well, that will give you, if the mean is 10, yeah, if you took 10 times 14 minus the total of the data entries, you're just going to get 0, right? Because the total of the data entries is 10 times 14. That's exactly what it means for the average to be 10. So if you add these all up, you're going to get exactly 10 times 14. You're going to get 140.
Okay.
Yeah, yes, sir.
Yes, Prince?
Yeah, pertaining to this absolute value, which we solve the absolute value of 9.9 minus 10, I think 10, yeah, okay, yeah. So
yeah.
What I'm thinking on is if we are working with this absolute value, will the number be subtracted inside before coming out, or can we just bring the number out of the absolute value? And if so, if we bring the number out of the absolute value, what will become of the negative number that is in the center?
Right. So no, so that's a good question. So the point is, every time you've got some negative number in here, you need to change it to a positive number. Because when you're doing this mean absolute deviation, what you're adding up is distances. And distances are always positive. So it's not good enough. You can't combine these negative numbers first. You have to look at each one by itself. And you have to, sorry, let me just mute. So you have to look at each one by itself. And you have to add them all up as positive numbers. This mean absolute deviation will always be positive, right? Because you're always taking a bunch of positive absolute values and adding them to each other and then taking the average. So it's very important to treat each of these like a positive number, even if it looks like it's negative inside, okay? So you have to turn each one into a positive number before you do anything with them.
Okay, thank you.
You're welcome. Other questions? Emmanuel?
Yeah, that happens.
Yes, Emmanuel.
The appearance of the number, the entry. I'm saying you wrote here 14, but when I check the number, they are 16. So I'm kind of confused when it comes to that error.
Oh, did I make a mistake? Hold on, let me see. I thought it was only 14. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm getting 14. Right, I think 3 of these, and then there's 9 10s, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 2 of these. I think it's 14. Yeah. So I think this should be 14 over here when we write it down.
Hello?
Hello, yeah. Marcus?
Hello?
Yes. Oh, Emmanuel?
Yeah, maybe in his feeling that, yeah, it's Marcus.
Yeah, Marcus.
Yeah, maybe he's feeling like maybe the 9.1 9.9 is a normal separate, but they are decimal number like 9.9. But it
Right,
is
yeah, the
14.
9.9 just counts as one number. Yeah.
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 Okay. Thank you, sir.
Okay, you're welcome. Okay, any other questions about this calculation?
Yeah, that.
Yep. Kaifala?
Yeah, when you deduct the means from each of the entries here, the result to get like this 0.1, 0.1 are the absolute deviation, or and then I did the absolute deviation and then you divide by the number of entries to get the average of the, I don't know. When you subtract the means from each of the entries. So
Right.
how do we refer to that? This 0.1, 0.1. How do we refer to that?
Yep. Oh, these are, I would call these, yeah, you could call them the absolute deviations. That's
Okay.
why this
Then
is
they
called
mean-
mean absolute deviation, because each one is an absolute deviation, and then you're taking their mean.
Okay. Thank you.
Yeah, you're welcome.
Yeah, I wanted to understand.
Okay. Okay, other questions? Okay, let's just do data set number 2 because that's a little bit smaller. Right, that's minus 10, minus 10, 1. So minus 10, 1, 10, 24, 25. We also, again, have that the mean is 10, also an exercise. And then for the mean absolute deviation, which I'll just abbreviate MAD, what do we have? This is the average of negative 10 minus 10 absolute value, 1 minus 10, 10 minus 10, 24 minus 10, and 25 minus 10. And so what is that? Well, we have negative 10 minus 10, that's negative 20, but we have to do the absolute value, so it's 20. The idea is that minus 10 is 20 away from 10. So we have 20 plus, then here we get negative 9, but we have to do absolute value, so it's 9. And then here we just get 0, 10 minus 10. And then here we get 14, and here we get 15. So plus 14 plus 15, And then we divide by the number of entries, which is 5. And this comes out to be, so this is 29. And then plus 14 is 43. And plus 15 is 58. So it's 58 divided by 5. And this comes out to be 11.6. Okay. All right. So in this case, again, the first data set, mean absolute deviation, very small number, 0.043. Second data set, mean absolute deviation, much bigger number, 11.6. Okay. So this is telling you that the second data set is more dispersed than the first one. Okay. The first one has this very narrow distribution. It's a very small mean absolute deviation, means on average, each entry is only 0.043 away from the mean. Whereas the second one is much bigger. On average, each entry is 11.6 away from the mean. Okay. All right. Any questions about calculation number 2? Yes, James?
Yeah, so that means if we are finding the mean average deviation, that means we are looking at the distance each entry get from the means, right?
Exactly. Yep.
So what's the effect on the data if each entry distance is longer? Like having the second calculation we did, we have the distance for each each data or each number from the means to be 11.6. Do you have any side effect on the statistics?
Yeah, so I mean, the further away the entries are from the mean, that means your mean absolute deviation is going to be bigger. It doesn't generally affect the mean itself, and it doesn't affect the median itself. So we'll actually see this. I mean, let me skip ahead for a second. But for the homework, this is exactly one of the questions. So what happens to the range and the mean absolute deviation and the standard deviation of a data set if all of the entries are increased by 5? And then what happens if all of the entries are multiplied by 5? So this is going to be a homework problem for next week to think when you do some transformation on the data set, like maybe you change the units or something like that, then what happens to these measures of dispersion? Okay, so maybe I won't answer the question. I'll just say that something happens and you'll have some time this week to think about it, and we'll go over it again next week.
Okay, thank you.
Okay, you're welcome. Okay, any other questions about this calculation?
It's okay, sir. We can move.
All right, good. All right, so let's move on. Okay, so let's talk about the standard deviation now, which is a little bit more complicated. So the standard deviation, which is much more used, if you read scientific papers that involve statistics, they're not going to be calculating the mean absolute deviation. They're almost always calculating the standard deviation. And so, so this is how it's calculated. So again, we start with a data set, and the mean of the data set is X bar. So same notation that we had before. And now what is the standard deviation? Again, you're calculating these distances, these xi minus x. But with the mean absolute deviation, we took the absolute values of all of them, and then we took the average. Here, what we do is instead of taking the absolute values, we square each distance. So we take the square of each distance. And then you take the average of the squares. And then at the end, you take the square root. That's kind of to cancel out the squares. So if you want to think about this, you think about this as the, say, the square root of the average of the squared deviations. Okay, so this is what the standard deviation is. You take all of these distances, but instead of just averaging them, you actually average their squares instead. Keep in mind that the squaring is still going to make everything positive, right? So just like the mean absolute deviation, these standard deviations always are going to be positive numbers, right? So The squaring is going to make everything positive. You take the average of these squares, and then because you squared everything, you take a square root to cancel out the squares. What this does actually is that it makes outliers a little bit more important. So if you have entries that are very far away from the mean, then squaring them is going to make them really count for a lot. So the standard deviation makes extreme outliers a little bit more powerful. They count for a little bit more in the standard deviation relative to the mean absolute deviation. Okay, so yeah, so this is the formula, and it's similar to mean absolute deviation, but it has this squaring and this square rooting that changes it. And I should mention that so this is the standard deviation over here. And then I should mention that there's a related quantity called the variance, which is exactly the same, except that you don't take the square root at the end. So the formula is the variance equals the standard deviation squared. Okay, and since the standard deviation has this square root on the outside, when you square it, all you're doing is canceling the square root. So you can think of the variance as the average squared deviation. So if you just take xi minus the mean for all of your data entries and square them all and then take the average, that's the variance. If after you take the average, you then go and take the square root, then that's what's called the standard deviation. Okay, so yeah, so this is the variance and this is the standard deviation. And so what we're going to do now is do the same calculation with the same two data sets of the standard deviation. And we should expect that for that first data set that's very undispersed, that the standard deviation should be much smaller than what we get for the other data set, which is a much more dispersed one. Okay. So let's see. So example, standard deviation of the two previous data sets. Let me just write it again. 9.9, 9.9, 9.9, 10, 10, 10, 10, 10, 10, 10, 10, 10, and then 10.1 and 10.2. Okay. So again, we have that the average is 10. So maybe I can look at the, what are the xi minus x's? Xi minus bar x. What are these means? Let me write them all down. So it's -0.1, sorry, -0.1, -0.1, -0.1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 0.1, and then 0.2, right? So now, so this is kind of like the first step for a standard deviation. We try to write down what are all the deviations. So what are all these deviations from the mean? So the second step, remember, is we have to take the squares, the average of all of the squares. So we'll call it, so maybe this first step is, write down all deviations from the mean. Okay, so step 2 is average the squares. Right, so for step 2, we would have -0.1 squared plus -0.1 squared plus -0.1 squared plus 0 squared plus 0 squared, so on. We're going to have 9 of these. And then plus 0.1 squared plus 0.2 squared. And all of this is going to be divided out by 14, right? Because we're doing 14 measurements. And what this turns out to be is, what is this? This is 0.01, 0.01, 0.01, 0.01, and 0.04. So this turns out to be 0.08 divided by 14. And let me just do that on the calculator. I don't need to do it on the calculator. This should be about 0.0057. Okay. So this is what we do with step 2. We take all these deviations. If it were the mean absolute deviation, we would just take the absolute values of all of them and then average them. But instead of doing the absolute value, for the standard deviation, we do the square of all of them instead of the absolute value. And so if we add up all the squares and divide by the number of measurements, we get this. So this here actually is, if we just stop here, what we have is the variance. But in general, for step 3, to get the standard deviation, we need to take the square root. And what happens when we take the square root here? We get the square root of 0.0057. And that I cannot do in my head. So let me see. So square root of 0.0057. And so this turns out to be roughly 0.075. Okay. So this is the standard deviation, okay? It's here we get 0.075 for a standard deviation. Okay. And in general, the standard deviation will always be a little bit bigger than the mean absolute deviation. Okay, that's not so obvious, but in fact, it's true. Your standard deviation is always going to be a little bit bigger than your mean absolute deviation. Okay, so there are questions about how we carried this out. And this is step 1, this is step 2, and this is step 3.
Hello, boss?
Yeah, James?
Question?
Yep.
Yes, I got a question.
Yep.
Yeah. So like I'm asking, so that means you say when we stop without finding the square root of the value we stand at, we got the variance, right?
Mm-hmm. Yep.
So why is it, if you start the variance, why is the effect of that on the data, on the statistics, I mean?
So the variance and the standard deviation give you the same information, right? Because one is just the square of the other. So the reason that sometimes people use the variance and sometimes people use the standard deviation, so it matters a little bit more in advanced statistics. But for instance, if you multiply, so this is something you'll prove in the homework, but if you multiply, let's say you double all of your data. What's it like? You multiply all the data entries by 2. It turns out that what's going to happen is that the standard deviation will get multiplied by 2, but the variance will get multiplied by 4. Okay, so the variance scales with like squaring all of your data. And so it turns out that the variance is a more natural thing to use when you're dealing with what's called normal distributions and independent random variables. So it's kind of like when you're doing some more advanced statistics stuff, there are contexts where it makes more sense to use the variance because your formulas for how things work with the variance are nicer. Normally, when you're just writing down, doing some descriptive statistics, like here you have some data set, you've done some science experiment or some survey, and you want to present the data set, usually what you present is the standard deviation. And maybe you can think about this with units, like if you do physics or chemistry or something, the standard deviation is in the same units as the data entry. So if your data is measured in inches, then your standard deviation is also measured in inches. The variance is in the square of the units. So if your standard deviation is measured in like kilograms, then your variance is in square kilograms, which is sometimes a little bit less intuitive what that means, right? So what's good about standard deviation is that it's measured in the same units as whatever your original data was measured in. So that's why usually you report the standard deviation and not the variance. But the variance can be useful for certain types of formulas in more advanced statistics. So it's worth it to know what it is, but usually the standard deviation is the thing that you're going to do.
Okay, thank you.
Good. You're welcome. Other questions?
Yes.
No.
Yes.
Yes. Marcus?
For I think for the variance in the standard deviation is you have to calculate the variance before the standard deviation, right?
Yeah. You calculate the variance along the way to the standard deviation. Yeah.
Yeah. Okay. Thank you.
Okay. You're welcome. Yeah. So let me just write this swiftly. This is the standard deviation. Okay, other questions? Okay, let's do the other example, just the other data set. So I'll do that on another page. So what do we have? Our data set here is minus 10, 1, 10, 24, 25. And we again have that the mean is 10, right? First, you've got to calculate the mean. So let's do the first step. We have to write down all of the deviations. So in that case, we have minus 10, minus 10. So that's minus 20. Then 1 minus 10 is minus 9. 10 minus 10 is 0. 24 minus 10 is 14. And 25 minus 10 is 15, right? These are all of the deviations. Okay. And so the second step, remember, we average the squares, right? So we have to square all of these and average them. So we get this minus 20 squared is 400 plus 81 plus 0 plus 14 squared is 196. And then 15 squared is 225. And we take all of these and we divide by 5. And this comes out to be 481, 677, and then 877, 8. I'm getting 902. Is that right? Let me see. Want to make sure that's right. 400 plus 81 plus 196 plus 225. Yeah, 902. So
Yeah, it's correct.
Okay, good. So 902 over 5, which is equal to 180.4.
Yeah,
That's good. Okay, good. So 180 point that's okay, right? So 180.4, and again, remember, this is the variance. So if you just want the variance, then you're done. And then if you want the standard deviation, you just have to take the square root. So square root of 180.4, and that's going to give you square root of 180.4 is going to give you about 13.43. Okay, and so this here is the standard deviation.
Hello.
Yes, hello?
Yeah, Dr. Obers.
Yeah.
Something came to my mind when we were calculating the first, not the 5 problem, not the 2 problem on standard deviation, but the other problem we're calculating it.
The mean absolute deviation, this one?
Yeah, when we subtract the means from each of the data entry, the negative sign can be swallowed up. We don't include it in the data entry.
Right.
But when we come down to the standard deviation, we include the negative sign and affect
right. Well, you include it, but it doesn't matter, right? Because in the end, you square it. So if you don't want to include it, you don't have to. It's not going to change your answer, right? It makes no difference whether I write a minus 20 or a 20 here, right? Because either way, it's going to square and give me 400, right? So if you want to not include any of the negative signs, that's completely fine. You're going to get the same answer anyway, right? The whole point of the squaring is that it gets rid of all of the negatives. It means that stuff that's less than the mean still counts for dispersion, and stuff that's greater than the mean still counts for dispersion, right? It counts for dispersion for standard deviation, whether or not you're an outlier to the left or an outlier to the right. Okay. So, yeah. So the point is, it doesn't matter. You can write the minus sign if you want to. I usually do, but if you don't write it, you're going to get the same answer. It's going to be okay. Whereas with the mean absolute deviation, you have to remember not to write the negative sign, because if you write all the negative signs, you're going to end up just getting 0. And that's going to be wrong. So with the mean absolute deviation, you absolutely have to write down the positive number for all of the deviations. For the standard deviation, it doesn't matter because you're just going to end up squaring it. So whether or not you have the negative sign makes no difference. So is that okay?
It's okay,
Yeah,
thank you.
Okay, good. Yes, other question.
Yeah, I'm a
Manuel.
bit confused.
Mm-hmm.
In the 3 steps work in all problem,
Yep.
Because after averaging the square, you still have to apply the step 3. My question had to do because when we apply the step 2, you have from the step 2 you got to get the variance.
Right.
So if you happen to get a 0, can the step 3 still be applied?
Sorry, maybe I don't understand the question. So once you get the variance, if you want the standard deviation, you have to apply step 3. If you just want the variance, then you just stop at step 2.
Okay.
Does that answer the question?
Yeah.
Okay. Good. All right, great. Other questions?
Yes.
Yeah, Marcus?
Yes. Yeah. Now for the question my brother was asking, that maybe in your problem, they ask you maybe the standard calculate the standard deviation and the variance. So you are saying that if they say calculate the standard deviation, I mean the variance and the standard deviation, you have to apply the 3 method. But
Exactly.
if it is calculate the variance, you just have to stop at the variance level.
Exactly. Yeah. If you just want the variance, then you stop at step 2. If you need the standard deviation also, you have to go to step 3.
Okay, thank you.
You're welcome.
Yeah, Dr. Odud.
Yes, Ed?
Yeah, I have lay or maybe probably observation. Because part of the time we solve problem, I noticed that we just use on group data.
Right.
Because in statistic, we have on group and we have group. Like what you are finding here with the mean deviation, we're not solving any problem with group data. Can we go over any problem with group data?
Yeah, that's a good idea. Yeah, maybe we'll do that next week.
Okay,
so again, yeah. So what's going to happen with group data is, yeah, okay, we can do that. So, and I saw there was another question in the chat. I saw another question in the chat from Rufus about rules of formula for obtaining the class interval of an ungrouped data. I mean, that's maybe a little bit off topic for now. You know, to some extent, there's not really rules or a formula. You just have to decide what class interval is going to make better sense for your data. Maybe I'll say more about it next time when we talk about group data. But no, that's a good idea. So maybe next week we'll talk a little bit about doing deviations. So deviations meaning, you know, mean, absolute, and also standard with group data. Okay, so yeah, so yeah, why don't we do that? That'll be good. And again, it's one of these things where the formulas aren't exactly the same, right? I mean, like when we calculated the average of group data, we just had to kind of assume we just kind of assumed that everything clustered around the mean. So it's also here, like to calculate the standard deviation with group data, it's not like there's only one exact way to do it, but there are ways that are reasonable to do it and ways that are not so reasonable. So that's a good answer. It's a bit of an advanced topic, but I think it's worth talking about since we've done so much earlier on with group data. So we'll talk about that next week. Okay. Good. Other questions? Okay, so I mean, like these are the rules basically. Okay, so I guess we have enough time to talk quickly about these box and whisker plots. Let me just see what else is going on. Yeah, okay, so we have enough time to do this. So sometimes, so one last data visualization thing. So there's something called a box and whisker plot, or sometimes just a box plot. And it's a way of visualizing a data distribution that takes into account both its central tendency and its dispersion. And it's actually based on percentiles. So it's not really based on what we've talked about today. But what you do, I mean, I'm going to say all of this, but it'll make more sense when we do an example. So a box is drawn parallel to an axis. You can do it vertically, horizontally, we'll do it vertically. And the box stretches from the 25th to the 75th percentile of the data. And the length of this box is sometimes called the interquartile range. Okay, or it's abbreviated IQR. And then a horizontal line is also drawn at the 50th percentile, which is the median of the data. And then whiskers extend above and below the box to the maximum and minimum of the data points respectively. And then what happens is that you can read off the range and the median of the data directly from the box and whisker plot. Okay, so there are various variants of this. So where you don't draw the whisker all the way to the maximum and the minimum, there's different conventions for how people do this. But for now, let's use this definition. So I just want to do one example. So let's say we have the following data. So we have a box and whisker plot for this data. So what you have to do, so to draw, you need to calculate 5 data points. You need the max, you need the min, you need the 25th percentile, you need the median, and you need the 75th percentile. Okay, and remember the median is just the same thing as the 50th percentile. So let me do this. Let me do this fairly quickly. I'm just going to tell you here that we have that n is equal to 31. So there's 31 measurements here. And so if you remember our percentile formulas, so 25th percentile rank, what you do is you take 0.25 times 31 plus 1. So that's going to be equal to 8. And so what you actually do for the 25th percentile is you just take the 8th entry. In this case, it's an integer, so we don't have to do any of that averaging. So we get 1, 2, 3, 4, 5, 6, 7, 8. So here we get 62. So 62 is the 25th percentile. Similarly, 50th percentile rank, otherwise known as the median, is 0.5 times 31 plus 1. This is equal to 16. So we have to find the 16th entry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's going to be 71. Is the 50th percentile. And then lastly, 75th percentile rank is going to be 0.75 times 31 plus 1. That's going to come out to be 24. We need the 24th. Well, here the 71 was the 16th. So 72 is 17, 18, 19, 20, 21, 22, 23, 24. So we get 76. Okay, so the information that we need for this box and whisker plot is the max, the min, the 25th percentile, the 50th percentile, and the 75th percentile. So here the max is 100, the min is 45. That's the smallest data entry is 45. The 25th percentile is 62, the 50th percentile is 71, and the 75th percentile is 76. So I'm just going to copy this data, and then I'll show you how we just draw a very crude box and whisker plot by hand. So let me say here we have, so what was it? Max equals 100, min equals 45, 25th percentile, it was 62, 50th percentile was 71, and 75th percentile was equal to 76. So what do? You just have an axis that more or less you can mark from the bottom of your range to the top of your range. So maybe we'll mark this every 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll mark this 10, 20, 30, 40, 50, 60, 70, 80, 90. And then for our box and whisker plot, what I do is I draw a little box that goes from the 25th to the 75th percentile. So from 62 up to 76. So maybe I'll draw it in different colors. So I'll go from 62 here up to 76. So I'll draw this as a box. 62 up to 76. I draw a line at the median. So I draw a line across that at 71. This is the box. And then the whiskers, I draw little lines that go all the way up to the maximum and all the way down to the minimum. So this is the maximum here. It goes up to 100. So this is a whisker. And then all the way down to the minimum here, it's 45. So this is also a whisker. Okay, and this is the basic box and whisker plot for my data. So what it shows you is kind of where the data is centralized. This is where the median is. The box is where kind of the middle half of the entries are. So the interquartile range here is 76 minus 62. So that's 14. And then the whiskers show you kind of like where all the outliers are. Everything that goes from the bottom to the top over here. Okay. Okay, so this is it. This is how you draw a box and whisker plot. You need these 5 numbers in order to be able to do it. Okay. And once you have these numbers, you draw a box from the 25th to the 75th percentile, put a little line at the 50th, and then whiskers going up to the maximum measurement and down to the minimum measurement. Okay. So this is what's called a box and whisker plot. And in fact, maybe I don't want to rush it. So maybe we'll do it next time, but next week it can show how to do this in Excel. So Excel can make a box and whisker plot for you, and so we'll show how to do that next week. Because I don't want to rush that. So yeah. So any questions about how we do this plot? I know it went a little bit fast.
Hello.
Hello, Marcus.
Yeah, thank you very much. And like for the beginning today, I've understood what all you have said. But from here, I think you said next week because I'm not even understanding even the marks, no, the meaning. I think next week I'll have to capture it well because I'm not really understanding. This is my first time you come across. Yeah.
Okay. All right. Yeah. So we'll talk about it a little bit more next time. The problem was we did percentiles like a month ago, so I didn't get a real chance to take the time to recall, but I can do that again next week if we want to. You need to know percentiles to draw these box and whisker plots.
Okay.
Good. So let me just say, okay, so you can also do this in Microsoft Excel. We'll use the above data as an example, but this will be next week because I don't want to rush the technology. And then the max represents the largest number and the min represents the smallest number. Yes, Armstrong. Thank you. Yeah, so in this case, for this data, the largest number is 100 and the smallest number is 45. So that's what we get for the box and whisker plots, goes down to the smallest and up to the largest. Okay, so we'll do that for computers next week. We'll talk about group data for standard deviation. And so here's the homework exercises. So first, calculate the range, the mean absolute deviation, and the standard deviation for just this basic data set, 1, 2, 3, 4, 5, 6. And then 2 is more conceptual questions. So it's really 6 questions in one. So what happens to the range, the mean absolute deviation, and the standard deviation of a data set if all of the entries in the data set are increased by 5? That's the first question. And then the second question is, what happens if you multiply all the entries by 5? And so notice I'm not giving you a data set there. I'm asking you for a general rule that will apply to all possible data sets. Okay, so I want to know if I have any data set and I then multiply all of the entries by 5, can you tell me what will happen to the standard deviation? Right? Can you tell me what will happen to the mean absolute deviation and what will happen to the range? Okay, so this is a bit of a challenge. It's a good thing to think about. When you're asked an abstract question like this, it's good to start with an example, right? Start by writing down some simple example, maybe a data set with only 3 entries or something like that. You can do a simple example and you can see what happens, and that will suggest what you think should happen in general. But to answer the question, you have to actually show what happens in general. It's not good enough to just do one example, right? So one example is how you start trying to figure out what happens. But a full answer to this is really a proof that it works in general. Okay, so we'll talk about that next time. I'll send this out, later today, so you'll have a copy of this. And then lastly, so I'll say next week we'll summarize what we've learned about statistics, but we'll do a couple more things. We'll do box and whisker plots in Excel, and we'll do deviations for group data. And we'll do deviations for group data. And then maybe, you know, we're not going to be doing much about geometry, but we'll do a little introduction to plane geometry. Okay. All right. So I think that's it for today. So we did, you know, all these deviations, these measures of dispersion, and then also this box plot, which is our last data visualization technique, which kind of helps us visualize data. Remember, we've had histograms, and we've had bar charts and bar graphs and pie graphs and histograms and cumulative frequency diagrams and all sorts of things. The nice thing about the box and whisker plot is it gives you everything in one kind of compact diagram, right? Whereas if you had a histogram for this data, you'd have to draw maybe 5 bars or 6 bars, and it would take up a lot of space. The box and whisker plot really gives you everything in one kind of small diagram. That's why people like it. Okay, so any last questions?
Thank you for today.
Okay, you're welcome. Let me turn off.
Thank you so much, sir, for the problem.
Okay, you're welcome. By the way, and one more reminder, please write down your name in the chat if you have not done so, because we want to make sure you get your data sent. And if you don't write yourself in the chat, then we don't have your record for attendance. So if you've written anything in the chat, then you're fine. But if you haven't typed something in the chat, please do so before I stop the recording, because I'm going to stop the recording in 1 minute, and that's going to be the attendance that we have.
Wow, thank you very much.
All right, you're welcome, Harrison.
Thank you, Dr. Obers. I really appreciate it.
You're welcome, James. Thank you for all of your questions.
Good, Andrew.
Hi, Sanjay.
Yeah, how you doing?
Good. How are you?
I'm doing great.
Good. Yeah, so sorry, I'll get you the attendance much faster this time. I'm sorry for waiting until today.
Okay.
Okay. All right, so I'm going to go stop the recording now.
Yeah, Andrew.
Yes?
Andrew.
Yes?
Yeah, thank you very much for the day.